So this video is still on the chapter of determinants. We have been introducing the concept of permutations, inversions, transpositions, etc. Well, after the introduction of all these concepts, André Vitor, a friend from Brazil, gave me a very nice idea to show a very nice application of all these concepts. So this will be still on permutations. Okay. So this was the all very nice idea of André Vitor's. I think you might know this famous 15 puzzle, also called the gem puzzle or boss puzzle or game of 15. When I was a kid, I remember they selling these small boxes with this game of 15, they call it, or the mystic square, but they call it mystic square to so many things that I would not use this one, but okay, and many others. So this is a sliding puzzle that consists of a frame of numbered square tiles in random order with one tiling missing. Okay, let me show you one image. Here you are. You have this example that André Vitor sent me. So we have an image of a box. Okay, we have 4 by 4, so 16 slots or houses or holes, right? And one is missing. Okay, so in this case, sometimes they have some kind of image here. It can be an actor or a building, something like that. So, but we are going to do this with numbers. So in this case we have 16 boxes, but we have numbers from 1 to 15. Okay, so this is the whole idea. So you know what I'm talking about now, about when I say the 15 puzzle, right? So this is a sliding puzzle. In the previous example we saw a 4 by 4. Okay, it consists of a frame of numbered square tiles in random order, okay, with one tile missing. In the previous case was a 4 by 4. Well, here you have a case of the 15 puzzle. Okay, so play the 15 puzzle online. I am sure you will get 100 of these links, but I can put these links on the video. So here the puzzle is solved, right? 1, 2, 3, 4, 5, 6, 7, 8, etc. Right? Now you can scramble, and then you get this, okay, and now you try to solve it, okay, and you can do anything you want here, right? Moving the 4 upwards and then 4, 6. So the 6 is already at its right place, right? Now I have to bring 5 somewhere. Well, you're used to this, so you can scramble again and again and again, okay, and try to solve this puzzle. Okay. Now we have a very simple question. Can we solve this for any position? Well, there is an history behind this puzzle, and I'm not going to count all this, or to tell all this story, how it began and all that sort of thing, but only we are going to see the steps for the solution. So the first one who got an answer for this, or the first proof we got for this, was in 1879, Johnson, who gave us a proof. I might leave the papers in the link next to the video. And Johnson in 1879 proved that with odd permutations the puzzle is impossible to solve. We will see this in a minute. But in the same year, 1879, another mathematician called Story gave us a proof that with even permutations the 15 puzzle is solvable. Now, if you want a complete proof, although a lot of people did not believe that the proof would be showed, but Archer in 1999, using graph theory and other stuff in a very simple paper of 6 or 7 pages, presented a very simple proof. So in order to see if the puzzle is or is not solvable, you simply count the permutations inversions. Okay, and that is really simple. For the concept of inversion of a permutation, please check my previous videos. I think I have 4 or 5 or 6 videos before this one, only talking about permutations, inversions, composition and all that sort of stuff. Okay, let us pick this example. We have here a position 2, 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So we'll look at this from the permutation inversions point of view. If you look well, only this pair 2, 1 is the only inversion here, because this 2 is the only number that is at its right hand a smaller number, because if you look well, 3 has no smaller number at the right hand, 4 has no smaller number, 5 has no smaller number. So we look at all this as if it was only one line, okay, as if it was 2, 1, 3, 4, 5, 6, 7, 8, etc. And if you look well, the only inversion here is this 2, 1, right? So we have a odd number of inversions, right? So this puzzle is impossible to solve. If you want to try, just put it on some computer program and try to solve it. You will see that this is impossible to solve. Okay, let us look at another example. This one is going to be a bit more complicated because we still have to count a number of inversions. Okay, so this is a bit hard to count because, for instance, for 13 we have a lot of inversions. So 10 is 1. We are counting all the numbers at the right hand of 13 less than 13, the permutation inversions. Please check the previous videos for this. Another one will be this one, 13, 11, right? And this one. This looks very complicated and hard to write, but then you will see this is a small trick and you count this quite quickly. Okay, so then 13.6, 13.5, 13.7, right? All these are permutation inversions. At the end of the day, if you want to count them, it's really quick. You pick 13 and you count all the numbers smaller than 13 at its right hand. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So we counted 12 inversions for 13. Now we have to do the same for 10, right? So 11 is at the right hand but is bigger, so we pick 6, right? So this is 1. Then 5 is another, right? So 10, 6, 10, 5, 10, 7, right? 10, 4, 10, 8, 10, 1, 10, 9, 10, 3, 10, 2. So all these are the inversions of 10. So you pick 10 and you count all the right hand numbers smaller than 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 9 inversions for number 10, okay? Now let us do the same for 11. So I counted for 11, I counted 9 inversions. For 6 I counted 3, and this is correct for 6, right? Because there is only 5, 1, this was 5, not 3. So 5, 4, 1, 3, and 2. That's 5, right? For 5 there are only 4 inversions. 1 in 4, 1, 3, and 2. So 4 inversions. For 7 you also have only 4 inversions. For 4, 3. For 8, 3. 1 is no inversion, of course. No right hand number. No number at the right hand of 1 is smaller than 1, obviously. For 12 we have 3. For 14 we have 3. For 9 we have 2. For 3 we have 1, only 2, of course. And for 15 we have only 1. So 59 inversions, right? An odd number of inversions. Of course, this is I'm doing this on more or less a formal way, but then if you know what you're doing, you just count it. You pick 13, right? And you do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and you cut 13. Okay, then 12. Then you pick up on 10. Okay, 12. So 13. 14, 15, 16, 17, 18, 19, 20, 21, and you cut 10, right? So it's really quick to count then when you it's really basic stuff, this. So we have 59 inversions for this permutation. So again, this one can not be solved because there are an odd number of inversions. So you can go back to this application, play the 15 puzzle, scramble, you see, and check that all these ones, since they all are solvable, they all have an even number of transpositions, otherwise they are impossible to solve. A very funny fact is that Bobby Fischer, Robert James Fischer, the famous chess player, world chess player in 72, for many players and for many people the best chess player ever, he was an expert at solving the 15 puzzle. He had been timed to be able to solve within 25 seconds, and this is absolutely amazing. Fischer demonstrated this on November 8, 1972, on a program called The Tonight Show, starring Johnny Carson. I don't know if there is a video for this Tonight Show starring Johnny Carson with Bobby Fischer. I've watched this. This is very old. I've seen Bobby Fischer on some other TV shows, like the famous Dick Cavett and all that sort of thing. Okay, so this is a very very touching fact for me, since Bobby Fischer was really a great chess player. I'm sure that if you get on YouTube and you hit something like how to solve a 15 puzzle, you're going to get a lot of answers for this. Another very interesting question around this, but this is already a generalization, is what is the maximum number of moves required to solve this n by n generalization of the 15 puzzle? Well, we are going to get into a sequence, so if you go to that Sloan's Encyclopedia of Sequences, it will be there. Here you are. So the square array read by anti-diagonals, Mn, maximal number of moves required for the M times N generalization of the sliding block 15 puzzle or 15 puzzle. Okay, so if M is 0, then this is 0. If it is 1, that the minimum number is 1, etc. Okay, so you can consult this. So this is for those used to this is sequence A 15 19 44. Please check this number, okay, on the online encyclopedia of integer sequences. So the final answer is, can we solve it for any position? Yes, if the number of inversions is even and not possible if odd, if the number of inversions is odd. Okay, and thanks again to Andre Witter. I would never do this if it was not him.